Welcome to today's webinar. We will look at reinforcement and design of concrete surfaces today and how this is done in RFEM. My name is Gerlin Schubert. I'm the presenter today, and my two colleagues Alexander and Adrian, Alexander Meyerhofer and Adrian Langhammer, they will help me with the questions. We will look at the concrete slab that you see on the right-hand side. You will see how you can easily calculate your required reinforcement and design checks with our module family for concrete design. This is the control panel of the GoToWebinar, and you can show and hide the control panel by pressing the orange button up here. And this is the most important bit down here. Use the chat option to ask your questions. Please do not hesitate to ask questions. Alexander and Adrian are happy to answer them. We will first talk about the concept of the add-on module family for the design of concrete structures. I will then explain you the new features in the add-on module out of concrete surfaces. So we have improved it a lot in the recent version. And we then come to an example. The main part of the webinar is an example presented in RFEM using RF concrete surfaces and RF concrete deflect. It is an example of a concrete slab, and in this example I will show you how to define reinforcement, how to design in accordance to the Eurocode 2, how to do an analytical deflection analysis with RF concrete deflect. Of course, we will also look into results, and I will show you how to export the reinforcement data. Let's get started with the concept of our module family for the design of concrete structures. The RF concrete is split into two modules, the RF concrete surfaces and the RF concrete members. And the surfaces is for the design of surfaces like concrete and slabs, concrete slabs, walls or shells, and the RF concrete members is for the design of members. In both modules, the ultimate limit state is proved. The required lateral reinforcement is calculated for bending, shear, and torsional loads. This is chapter 6 of the Eurocode 2. The RF concrete members is doing also the shear at interfaces. Also in both modules, the serviceability limit state is analyzed. Here the stress limits of steel and concrete are analyzed and the crack width is proved. This is described in chapter 7 of the Eurocode 2. The RF concrete members is doing also a deflection analysis, which is using the analytical solution as described in section 743 in the Eurocode 2. The RF concrete members is also doing a structural fire design in accordance to Eurocode 2 part 1-2. So these are the basic concrete add-on modules. You can add the deflection analysis for surfaces with RF concrete deflect. This contains the analytical solution in accordance to the Eurocode 2 section 7.4, and this deflection analysis is available for the uncracked or the cracked state of the concrete, so state 1 or state 2. We also have a nonlinear analysis for concrete surfaces and members available. In RF concrete NL, we perform geometrical and physical nonlinear calculation of deformations for the serviceability limit state. Long-term influences like creep and shrinkage can be considered. Stresses of steel and concrete can be calculated. For members, also the ultimate limit state is checked, so you can perform stability analysis with the general method. This is described in section 5.8 in the Eurocode 2. And you can perform, for example, a nonlinear bending analysis. RF concrete NL is calculating results in an iterative process, so it's a nonlinear algorithm. It gives obviously more exact results, but the calculation takes longer. So this is this module. And the RF concrete deflect calculates deformations with an approximate method, and therefore the calculation is faster. So it really is depending on the model and your needs and your requirements. Furthermore, you have some add-on modules for columns. This is the RF concrete columns. This performs a stability proof based on the nominal curvature. This is described in section 588 of the Eurocode 2. We have the RF Punch Pro. This is for the design of punching shear resistance. This module was just recently released, so it's quite new. And you can have a look and you can always test our software. You can not only design the punching at column ends, you can also design wall endings and corners. And last but not least, you have the RF Foundation Pro. This is for the design of foundations, and you can design for single buckets and for block foundations here. For those who are using the RF concrete surfaces already, I want to summarize new features that we just released in the latest customer versions in the 70703. This is the most recent customer version. And here we made quite a few changes in the serviceability limit state. You can now consider more than one design situation in one module case. You can individually select your required analysis method, and you can now distinguish, you can define separate concrete tensile strengths for the minimum reinforcement and for the limitation of crack width. Prior, you defined only one global concrete tensile strength, and that was it, and now you can separate between these two cases. It's very important, and you often have to decrease the concrete tensile strength in case of the crack width design. We also improved a lot regarding the definition of the available reinforcement. So prior, you were able to do an automatic arrangement of additional reinforcement, and now you have a user-defined option for the definition of reinforcement regions. So you can define your own single regions and define which reinforcement is in which region. So we will see this in our example. We will define those regions and use this feature. We also improved the graphical result evaluation. You can see the reinforcement which is additionally required to your user-defined minimum reinforcement. You can also see the utilization of the defined lateral reinforcement. This is something you will also see in the example. The reinforcement regions can be accessed via the COM interface, and you can now export the isobans, so these colored surfaces that you know from our result view. You can export this into the DXF files that you can use in nearly all the AutoCAD softwares. So we already start with our example. We now move on to the practical part of this webinar. We study a flat concrete slab, and we will go together through a workflow which you are very likely to use in your practice as well. So I will first, of course, I have to explain you shortly how the model is defined. I predefined some loads, and I did already the load combination to save some time, so I will quickly show you this. Then we will design the ultimate limit state, and we do this to determine the basic reinforcement that we need, and we will use this basic reinforcement then for our first design of the serviceability limit state. We will notice that this is not enough in some of the regions, and we have to add some more reinforcement. Therefore, we will use the new feature user-defined reinforcement regions. We will do a deflection analysis. We have to increase the thickness of the concrete slab to fulfill the deflection limits. And finally, we will export the reinforcement results. I will, in between and at the end, I will give you always some additional options and hints. I switch now to RFEM. So we consider a flat concrete slab which is based in an office building with a thickness of 26 centimeters. The concrete slab has an overhang here about 26.5 meters. I switch on the dimensions so that you see, so the overhang is 2.65 meters, and we have The distance between the supports is 5.50 meters in the first field and 8.20 meters in the second field. So 5.50 meters is this field and 8.20 meters is this one here. I have already entered the structure in RFEM. I've also entered the loads and saved them in different load cases. The load case 1 contains the self-weight. You see it here already. So here the load is just uniformly distributed, and I've defined some imposed loads in the load case 2 to load case 5. And here I've varied the imposed loads field by field. To define the loads, I've used 3 variable loads. When I double click on one of those loads, then the added free rectangular load dialog is appearing, and you can enter the magnitude here, and you can select any free variable region for the definition of the load. So this is a quite flexible feature for the definition of loads, and this is not only available for rectangular loads, it's also for circular and so on, so for many different shapes of loads. Okay. I've used automatic combination options that are available in RFEM, and I will show you this quickly. So you switch it on in the data navigator, and then when you go onto the file naming, click right, then you see general data here. You open the general data, and in here you have the classification of load cases and combinations, and I want to combine the combinations automatically in accordance to the Eurocode 0, and I do not want to use a specific national annex here because you are coming from so many different countries. I just used the European recommendations. So this is the place to switch it on, and here in the Edit Load Cases and Combinations button, a dialog appears again, Edit Load Cases and Combinations. You see what RFEM is actually doing. So these are the load cases that I have defined. Then you have 2 different actions defined by RFEM automatically, the permanent and imposed loads. It does 4 different types of combination expressions, 1 for the ultimate limit state and 3 different types of serviceability limit state. So one is the characteristic, frequent and quasi-permanent. And then RFEM defines some basic rules for the combination and finally generates all the different load combinations for the ULS in red and for the SLS in green. It does also create some result envelopes which come up here in these result combinations. This is just what I wanted to show. I switch off now the dimensions. You can do it here in the display navigator, the dimensions off. You can also right click here in the main window and can show or hide the dimensions. I change also to a wireframe model. This is done here. At the moment we look to the solid display model, and you can change it here to wireframe, and I change also to the view in Z direction here. So it's now time already to open the RF Concrete Surfaces module. I open it and I change to the European recommendations for the same reason. I do not want to use a specific national annex. And we start with our first case. We do first the design for the ultimate limit state, only to get an idea of the required reinforcement. This is the first consideration, the ultimate limit state without defining any basic reinforcement. So I'm going to select the loads for design. So here down we have some filters, and when you choose the load combinations of the ULS, ultimate limit state, then you have only the load combinations in the list that are relevant for you now, and you can select all. I don't want to have the sulfate. You can select all and have all load combinations of ULS selected for design. So this is all for here. Then we go to the materials table. The concrete class is overtaken from RFEM automatically. And here you have the reinforcement steel, which is B500S with ductility class A. This is something you need to choose here. And the next table, the surfaces. This is just a summarizing list showing you different surfaces that you have in the model, and the thickness is overtaken from the RFEM model. In the reinforcement table, you have some reinforcement ratios. These are some predefined values from the standard, and I don't want to change them here. Then you have the reinforcement layout. Here's the place where you define the thickness of the cover for reinforcement and the directions of the reinforcement. So I'm going to choose a cover according to standard, concrete cover for reinforcement according to standard. And I go to the edit button here, and as my concrete slab is inside in an office building, I have the exposure class of XC1. So I choose this, and the concrete cover is automatically calculated with 2.5 and 3.5 millimeter. So I click OK, and this is something automatically entered here. And I measure this from the center of the reinforcement bars. This is set here, centroid of reinforcement. Then we go on to the longitudinal reinforcement. I do not want to define here anything for now. We come back to this later, and here's the place where you define your own user-defined reinforcement regions. For now, we study the ultimate limit state, and we just want to have an idea how much reinforcement I actually require. I do not want to provide any basic reinforcement right now. These are the settings in accordance to the standards. So we keep this as the default values are. We want to use the so-called flexural reinforcement. This regulates the minimum longitudinal reinforcement for plates. We also want to use the shear reinforcement. And here on the right-hand side, the partial factors are defined, are set again, and we keep them as they are. We are now ready for calculating the ultimate limit state. And the result tables, here you get a summary of the results, and the required reinforcement is listed here. You can either display this for FE nodes or for the grid points. More interesting is the graphic. So when you click on the graphics button, you jump into the graphic directly, and you have the results navigator open, so you can have a look to the several reinforcement directions, and shown at the moment is the required reinforcement and the top reinforcement in the one direction. You see the direction arrow here, this little red direction sign, and for the AS2 it's showing in the other direction. Obviously, as expected, the top reinforcement needs to be highest at the column ends. So here underneath are the supports, and here is the place where we need the most reinforcement. And then we have the bottom reinforcement here in the one direction, and in the two direction we have those values. Here we have a few constant areas, 3.47. I emphasize this number because this is a minimum reinforcement that we are going to use for our next step of calculation, where we want to define the serviceability limit state, and we are going to define a basic reinforcement, and we will use the 3.47 as a basic requirement for the reinforcement. You can have a deeper look into the result by defining sections, and you can define sections here. New sections numerically. You can also open this, and then it's this here, create sections numerically, and you can give it a name, whatever. You can select your nodes, the edge points of the sections, and you can just select something from the graphic like this. Then the coordinates are automatically entered here in the edit fields, and you can select the direction of the shown results, so global and X, for example. I'm not going to finish this. I have prepared some sections for you here already, and I'm going to show you those. I have a long list already, and when you switch off the isobars up here, isobars off, and switch on the sections, which you can either do here in the main toolbar, or you can select the checkbox here on the results navigator. You activate it, and then you see the sections that I've defined. And for a better overview, I switch off the values on surfaces. So here you go. This is the bottom reinforcement, AS1 bottom, and you have these values, and this is the axis R. So I defined along the vertical lines, and I've also defined something in horizontal direction like this. And you can again switch in between, and when you look, for example, to the bottom one, you see, as expected, the highest values are close to the columns, and we very likely need more reinforcement here in these areas. Okay. This was the design for the ultimate limit state, and we have calculated the required minimum reinforcement. I'm going to switch back on the isobars and to switch off the sections. And I just want to remind you on this value, 3.47. We keep this in mind. And we go back now to the RF concrete surface module, which you can either do here in the data navigator or here in the panel on the right hand side. You see also a button, RF concrete surfaces, which opens up the module as well. So I'm going to copy this case. You don't have to copy it. It's just to make clear that we are moving on to the next step of the workflow that I want to describe today. This is the basic reinforcement. And I click OK. I've copied it to overtake all the settings that I've made so far. And I go now to this tab Serviceability Limit State here. And I select all the green load combinations for the Serviceability Limit State. I move them over to the selected for design. And I go here to the settings of the Serviceability Limit State and do some further settings. I want to do the design of cracks. I want to do the design of concrete stresses. I want to do the design of steel stresses. And so far, we keep this checkbox for deflection with RF concrete deflect clear. We use this later on in the next step of our workflow. For now, we keep it off. Okay, that's all. And I do not want to increase the required longitudinal reinforcement automatically for the serviceability limit state design. That's because first I assume that we need not more reinforcement that I've defined for the ultimate limit state. And the idea here in the webinar is to show the so-called not covered reinforcement. This is a new feature that we have available, and we will see, well, where we have to increase the reinforcement. So in which regions do we need more reinforcement? And when I would select this checkbox here, then RF concrete surfaces would automatically calculate more reinforcement due to the serviceability limit state, and that's not what I want in this special webinar here. I want to show you the not covered reinforcement. So, okay. I also want to emphasize here, as you know from the Eurocode 0, you have characteristic, frequent, and quasi-permanent. And now the Eurocode 2 distinguishes between a characteristic with direct load and a characteristic with imposed loads. This is a distinction due to the Eurocode 2. This is defined in the Eurocode 2 section 7.2. And in this example, there are no imposed deformations involved. So we keep the setting characteristic with direct loads. But when you have some imposed deformations, then you need to adjust this here manually for the specific load combinations. This is okay for us, and I go to the details to just show you what it actually means. The characteristic with direct load uses the factor K3, and the characteristic with imposed deformations uses the factor K4. And here's also the place where you decide which specific designs you want to do. You can switch it all off and just keep one single design check active if you want. Okay, then you can also have a look here when you don't know the factors for your specific national annex or also for the European recommendations. You can go in here, you can edit the parameters of your national annex, and here all the parameters are listed. And for example, you have the serviceability limit state, and here you have the factors K1, 2, 3, and 4. Okay. We move on to the surface table. We defined materials already, and this table did change now. Previously it was only a very small table, and now it's far bigger, and 2 tabs are added here. We have stress check and limit of crack width now, and we want to perform the stress check in accordance to the standard, so we keep with these settings. And in the limit of crack width, we want to define the crack width limits according to the Eurocode 2, section 7.3, and we have to choose here our exposure class XC1 here and here, and we assume that effects due to the heating that comes from dehydration do not apply here, so I switch this off. Okay, I go on to the next table, reinforcement. The reinforcement ratios and the reinforcement layout settings stay the same. In the longitudinal reinforcement, we define now our user-defined basic reinforcement. This is still a uniformly distributed basic reinforcement. So we had the number 3.47 square centimeter per meter cross-section of reinforcement. We wanted to keep it in mind. So I go to the library here and want to choose a Q mesh, a Q424, which has more cross-section of our required 3.47. So I want to apply this for the top and for the bottom reinforcement, and I'm pressing OK. Here is an info button to show you what it actually means. We distribute our basic reinforcement all over the surface. It's uniformly distributed. Now we are ready to perform the calculation. And you get an overview now here in the serviceability design tables. You have a summary table, and you get an overview of the performed design checks. The concrete stress is too high, obviously. You see, when I move this a bit down, then you see the red arrow here in the graphic. You see where the problem actually is. The red arrow and the add-on module are interacting, so you can always see in the graphic where you are. And this problem here is very likely due to a singularity. Oh, can I not? Okay, no, I can't zoom in right now because I have the module open, but it's here at the columns ending, and at those regions, singularities are quite often appearing. All other design checks are okay. So the steel stress, the diameter, the distance between the bars, and the crack width. So when we go into the graphics, then we can have a look to our service limit state design in the results navigator, and we can have a look to the ratio. So the ratio for the concrete stress is overloaded here in this area. That's what we have seen already. Then you have the steel stress. Here the design check is okay. You have the diameter, the distance between the bars, and the crack width. And you can have a more detailed look to the crack width in here. This is separated for all the different directions and top and bottom and so on. Okay. So what have we done now? We have defined the basic reinforcement, and we have calculated this in our first step with the ultimate limit state, and we have used this minimum required reinforcement as a basic reinforcement. And with this basic reinforcement, we fulfill all the required design checks in the serviceability limit state beside the concrete stress, and this is something we clarify in a moment. So we go back to the concrete surface module. Again, you can do this in the data navigator, or you can open it here via the panel. And now we are going to use user-defined reinforcement regions. We define our own regions and improve our basic reinforcement. I go directly to the reinforcement table now, and I go to the longitudinal reinforcement. This is still the tab that we have seen earlier, and I'm going to details here, the global details of the add-on module, and I change now to manual definition of the reinforcement areas. Earlier we had automatic arrangement according to the specifications in table 1.4, and now we change to manual definition of the reinforcement areas. I click OK. And now you see that the tab has completely changed. Prior it was only to define one global defined basic reinforcement, just as we did in the example so far, and since the most recent customer version, it is possible to define user-defined reinforcement regions, and this is this part in here. You can define rectangular, surface, polygonal, and circular reinforcement. And the input is very similar to what we have seen at the beginning of the example by defining 3 loads in RFEM. So the dialog is very similar. So I go in here, and it's a similar procedure as well. So first we define a mesh reinforcement that we want to use, and I have added here some user-defined meshes. So you can do this by exporting, importing user-defined databases. So I have saved on my computer a .db, a database. You can create this .db file by exporting here something that you have user-defined, and you can import it on any other computer. That's what I've did in advance to the webinar. So I have some user-defined meshes available here. So I prepared this before the webinar and choose now this one first. No, sorry, I choose this one. So, and what the numbers are actually meaning, that's what you see here. You have the distances of the bars, and you have the diameters, which are 8.5 and 12. So there are the numbers coming from, and here you see the final cross-section of the reinforcement. This is a top reinforcement that I want to define. And I can click OK. This is now loaded in here. And I'm now going to choose the region where I want to define it. So I go on onto this button, select both corner points of the rectangle, and I go from here to select the whole surface. So this is the first. I click OK, and now when I go onto this edit button here, I come to a table. Oh, I did something before the webinar here. I'm going to delete this row. This is not what we need. So this is the one we've just defined. This is, here you see everything you did. Location is top, the coordinates of the region. Its type of reinforcement is mesh. Here is the name of it, and when I click on this eye here, I come directly to my main graphic, and now I can have a look interacting. I can even move the table on a different screen and so on. And I can use also the buttons down here to define now even more reinforcement regions I want to define. And I show you this now, not covered reinforcement, When I click onto this, we have now defined a top reinforcement for the whole surface, but we see that there are regions where not the required reinforcement is not covered. So especially above the columns, this is what we have expected. So I'm going to define more regions here. So I'm going back into my table and create a new reinforcement. And I'm now defining some bars myself to show you also this feature, and especially to show you the little calculator that we have here in the background. When you open this, you can enter the diameter and distance that you want, the distance between the bars. And here, the reinforcement area is automatically calculated. This is again something we want to apply at the top, and I click OK. And now I have to select my region, and now I'm going to use this button here, select the rectangle via center, because that's now much easier. I can select the center of the column and move on and define this region. Important to know here is that each finite element where the center point is within the selected rectangle is included. You will see later that the free chosen reinforcement is oriented along the borders of the finite element measures. I click OK because I want to have a look again to my graphic, and I want to have again a look to the not covered reinforcement, and I still see that some parts are not covered. So I'm going to define a smaller surface on top, a smaller region here again to add some further reinforcement, but only on top of the column. So I'm going back in the table, click new again, and what I forgot, I have to add first the same as I just did, but have to enter the other direction. So far I only did the direction 1, which is defined here, and I have to add my second direction. When I use this button here, apply, then you will see that the table is just getting another row with the same definitions, but just in the other direction. And now it's time to create the smaller region that I was talking about. So I switch back to the direction 1 first. I enter a double 10, a double bar here, and the 70 as a space. And I select again a region from the center of the column to this. I have created little help notes here, as you see. And I can apply this again, and another row is added in the table, and then I have to do the same for the second direction, and now I can click OK as I want to close the dialog. So now we can double check again the not covered reinforcement, and now you see the column, and it's happy now with the reinforcement that we have defined. And we have to take care now of the other 2 columns. And here's something very nice that we have implemented. When we go into this table, I can select all 3 rows with the Shift key on my keyboard, and I can use these are 4 rows I have to select. Yes. I can use the Move and Copy with Offset feature here. And you know this from RFEM. This is the usual copy function that we have available on RFEM. So this dialog is the same as in RFEM. I want to create 2 copies, and here I can select the distance graphically. So I'm going to select the first point and the second point and click OK. And now the list is far longer, and you see the graphic is updating. And now I can double check again the not covered reinforcement, and you see the results are very much okay. You see here would be another region where we have to define something here, so at the wall endings and corners. But I'm not going to do all this now because it's the same procedure all the time. I have prepared something now in the background. So I'm just going to close here the module, and I have opened another file which is exactly the same, but here I've defined my regions already. And I'm opening the concrete surface module, and I'm going to show you the defined regions in here. Here's the edit button to open this table where we have just been. And I show you here now what we did. I can make the table far closer. I click onto the eye to show the graphic. And I also click onto the synchronization button here, which is very nice, as I can now, I move it all a bit, make this a bit smaller. So now I can show you what we actually did. I've defined also something for the bottom now, for the field 2, for the field 1. Then here, that's what we did together, the top definitions at the column, the large area, the smaller region, and we did the same for the other columns, and also for the third column. Exactly. And what I did then without you in advance is defining regions here at the wall endings. So, but it's the same principle, just that you don't have to watch me creating all the regions. Here's a filter option available in the table, this one, filter. So you could, for example, only look to the top reinforcement or only to the bottom reinforcement. This is something that is available. And this table, you can enter all the values here manually. You don't have to do it graphically. And very good is that you can access the whole table with the COM interface that we have available with RFEM. This is very nice too. So I click OK now here, and we are ready now for the calculation of our third case, the user-defined regions. That's the third case in our workflow that we look at the moment. And the calculation is done, and we could look to the serviceability design. It's still a similar, and we can have a look now to the graphics. And we can, for example, study the crack width, the overall crack width first. Yeah, so again, as we just did, you can have a look to all the single results here. So you just have to need to look through. You can again use these sections that we defined earlier and all these things. Now we go on to the next case and we'll calculate the deformation of our concrete slab. I go again back to the RF concrete surfaces module. So the RF concrete deflect that we are going to use now, I have presented it as an extra module at the beginning. It's not really an extra add-on module. It's integrated in here into the RF concrete surfaces. When we go to our serviceability limit state, to make clear that we start with the next step in our workflow, I copy again my case, and this is now SLF deflection analysis. And when we go into the serviceability limit state here and go to the settings of our SLS case, then I now activate the deflection with RF concrete deflect. And I want to consider all of them: creeping, shrinkage, and tension stiffening. Okay. And due to this activation, the surfaces table changed again. So we have 3 new tabs that appeared. We have the creeping, the shrinkage, and the deformation analysis. And in here, in the creeping, I have set, for the settings for creeping and shrinkage are the same. We assume a service life of 50 years of our concrete slab. These are 50 years. The hardening process of the cement is assumed to be slow. And the concrete age starts at 28 days. And the shrinkage settings are the same: 50 years, slow hardening, and these two settings. And in the deformation analysis, we have to define user-defined relative limits. We want to define them user-defined, and I define different limits for our 4 different surfaces. This is also the reason why I've defined different surfaces. When I quickly go with you to the graphic, I show you this was one surface and this is the other field, and I've defined separate surfaces for the overhanging part of the slab. This is exactly the reason for it. The reason is the deformation analysis. So in the surface back here, back to the deformation analysis, I want to define them user-defined and relative. So I'm clearing this checkbox down here. I want to define different limits for each of the surface. So I click in the table and select the first surface, and I'm going to select my distance. So the surface 1 is selected, it's highlighted, so I select the distance, the span. This is 5.5 meter. Is it correct? Yeah, it was 5.5 meter. This is correct. And it's L250, L divided by 250, which is the limit that we want to use. I click onto the next row, and I can do the same again. I select the distance, and it's the same limit here. So the maximum deformation limit is calculated, and for the overhanging parts it's a different limit. It's L over 100, and I select the span in this direction. And the last one, again, it's the same distance, and it's 100, and so it's calculating this. So I've defined the deformation limits, and now I can perform the calculation. We will notice that we are beyond the limits, that we are far beyond the limits, and we will have to change then our design. And there are 3 different options you have when you are above your deformation limits. It's quite common. So you're in such a surface design of concrete, and because it is often the serviceability limit state that is relevant and not the ultimate limit state. And you have 3 different options. You could, for example, super elevate the concrete formwork about 30 millimeter. You could also increase the thickness of your surface. That's what we are going to do. And the worst case would be to change and increase the reinforcement definition. The worst case, because this was quite a bit of work we had. So let's have a look to the graphic directly, and you have now deformations that are available here. Let me find them here. You have deformations, and we can have a look to the local deformations in Z direction, and you see the maximum deformation is 53 millimeter, and our limit was 30 millimeter or something, so we are overloaded. And we could have a look also to the section that we've defined here. So when I clear all these section checkboxes and activate the number 3, 4, I go to the result diagram directly. So here you can reverse the X orientation so that it's oriented the same way as we have defined it in our surface itself in the main graphic. So it's more logical, and you can use the increase button to increase this graph here, the result diagram. So it's overloaded, quite far overloaded, and we are going to increase the surface thickness as the easiest solution for us now, and we will see if this is helpful. I switch on back the isobands and switch, now that's actually not too bad, section off, and we go back to the RF concrete surface. module, and I copy again the case and call it deformation T is 30 centimeter. Oh, even I wanted to do 33 centimeter. Okay. And you can do it directly in the module. You don't have to change the RFEM model itself. You can, in the surface section here, surfaces table, you can change this to 33. So we are going to recalculate this and hope, cross our fingers, that the deformation is now okay. And after that, we only want to consider one last case. So far, we have calculated the deformation for the final state of the plate, and we have considered the lower deformation limits. There are some stronger deformation limits in the Eurocode 2 described, which is L over 500, and this is something that you have to use when you have some adjacent parts that could damage. So deflections that could damage adjacent parts of the structure should be limited. For the deflection after construction, the span over 500 is normally an appropriate limit for quasi-permanent loads. And this is the next case then. What we consider is described in section 741 in the Eurocode tool. But let's have a look to this deformation analysis now. So we reduced from 58 millimeter down to 24 millimeter, and that's okay as far as I remember the limits. Let's double check the limits. We have defined them in here. Our limit is for the cantilever. So for the overhanging part is 26. And it's 22 for the first surface where we are below, far below this limit. And in the surface 2 down here, we are also below the limit. And for the overhanging part of the surface, the deformation analysis is full fight as well. So we could have a look now also to the ratio of the deformation. And you see that we are below 1, or we are just at 1 here at the outer side of the surface. So we full fight the normal deformation analysis, which is okay for most of the cases. And we just get the question from customers very often, how can I do the more stronger deformation design analysis? So how could I consider the adjacent parts that could damage? So you could, when you go to the RF concrete surface, back to this, I copy it again and call this case now SLS deformation L over 500 as the stronger limit. The thickness of the plate stays with 33 centimeter, and we now assume a time of 60 days. That's the time when we build in the adjacent parts, which could be, for example, some light dividing walls. And we assume here the 60 days for shrinkage and so on. So what do we need to change? First of all, at this point, at this time, we don't have all these loads. We only have the self-weight load case. That's the first thing you can change. And then in the surface table, you change from the case 50 years down to 60 days. So we build in the light dividing walls, the adjacent parts, at the time of 60 days. So we have a creeping and a shrinkage, the same for shrinkage, 60 days. And we can now calculate this deformation, and then we compare both cases. And what you need to do to get your real deformation, which are relevant for the adjacent walls, for the adjacent parts, you have to build a difference between both cases, between the 50-year case and the 60-day case. So let's have a look to the graphic. Let's have a look to the deformations, to the real deformations. You set local here, and this is now the case we've just calculated. So I have a maximum deformation of 8 millimeters, and we remember the other case. We have all the different cases saved in here. You can always reopen them. And the other case was 24 centimeters. So we can build the difference. Let's have a look to the section as well. So I open the section and reverse the direction. We have the 24. Oh, that's not possible. Here it is. And the 8. And this is a difference of 15, 16 millimeter. So in this difference, this is the relevant deformation which needs to fall via the deformation limit of L over 500. This is something you have to check. And we have, for example, the Excel export available, so you can export all the data that you calculate with RFEM and also with add-on modules to Excel or any other software that you use for post-processing, and you can easily do a further analysis in there. The last thing I want to show you is the export option. When you go to File and Export, I want to show you that we can export our data to a DXF file, which is the radio button here. This can be opened in any AutoCAD software. And even more important, we have export versions, export formats to Glaser, ISB cut, for example, or Nemetschek, so software that is used for the further construction design of reinforcement. So you can export all these data, and then you can easily hand it over to the next person, to the planner, and so on. One thing you might have in your mind, you also need to do a punching analysis in this area where the columns ending is, and we have just recently added a new module, released a new module. This is RF Punch Pro, and here you can easily design the punching. And I just want to recommend the new add-on module RF Punch Pro, and here it is where you find it also again in the add-on module here. So now it's the point where I want to summarize this webinar. We started with the presentation of our add-on modules that you would need to perform a complex analysis of your concrete structures. We clarified how the modules are working together. Then I presented the new features of the RF concrete surfaces, which we have just released with the latest customer version. In the example that we studied, we went through the workflow that you would follow to find the required reinforcement to fulfill the ultimate limit state and the serviceability limit state, including the deflection analysis in accordance to the Eurocode 2. We hope that the concrete design modules of RFEM are interesting for you. Together with the modeling features, the nice graphical interface of RFEM itself, and the export options to software that you need for creating detailed technical drawings, this makes a perfect package for your concrete design projects. Why not test the add-on modules that I've presented today? You find more information on our website, or you can simply give us a call when you have further questions. And talking about our website, I want to emphasize that each of the webinars is recorded, and you can listen to them whenever you have time. There are some previous webinars about concrete, so I want to recommend the webinar which was held back in 2013. This is kind of the basic webinar. This is about design of concrete structures in RFEM 5. And we have a webinar about pre-stressing concrete. This was held back in December 2015. Amy Heilig, our CEO of the American office, offers a webinar tonight about the design of concrete members according to the ACI. And also the webinar that you just listened to is presented by Amy in end October. It's planned end of October to show you the design in accordance to the ACI. Today we did everything in accordance to the Eurocode 2. With these closing words, I finish the webinar. Many thanks for your attention, and we hope to welcome you again.